Alright, welcome to the next CSE 222 video, and in this video we're going to talk about sorts. We're going to go over a number of different types of sorts. We're going to look at these partially in terms of their order of complexity, how much work they do based on the amount of data that's being sorted, and we'll see some sorts that are order n squared, which is pretty inefficient, and we'll move up to sorts that are order log n or n log n, which will be much more efficient. And so we're going to start with a sort that probably people are familiar with. I think we touch on this in 121. We've talked about it before, and that's a good old bubble sort. And a bubble sort, it's honestly probably the only sort I've ever coded myself, because even though it's order n squared, you know, if you're not sorting 1 trillion pieces of data, who cares, right? If you're just trying to sort 100 or 1,000 numbers, n squared is perfectly fine. But it's a very inefficient sort because it's based on a pair of nested loops. And remember, if you have a for loop inside a for loop, that tends to be order n squared. But it's a good sort to start with. It's relatively easy to explain and to understand how it works. And the idea is basically, imagine a bunch of numbers, perhaps floating, and heavier numbers should be on the bottom, lighter numbers or smaller numbers should be on the top. And so we begin by making one pass through our data, and the goal of this first pass is to find the largest number and bring it to the bottom of the list. So this is an array, right? And it's got, let's just say, a set of integers stored in it. And so what we do is we compare the first two numbers to each other. And if the first number is smaller than the second, we don't do anything. Because, you know, if the second number is larger, it should be below the first number. So if this is, you know, a 10 and a 20, we're going to leave those alone. But if this first number is bigger than the second, we're going to say, oh, okay, that number is heavier. It should sink down below that 20. And so we're going to swap these two numbers. And this is going to be a 20, and this is going to be a 100. And swapping a pair of numbers takes, you know, a few operations. Copy this one to a temporary, and then copy this into here, and then copy the temporary into there, and you're done. Alright, so after we've compared the first two numbers, now we compare the second and the third number. And if this number is smaller than the one below it, leave it alone. If this number is bigger than the number below it, let's say this is a 30, then we're going to swap these two numbers. And this will become a 30 and a 100. And we're going to keep doing that. And when we're done, this number down here will be the largest number from the entire array. So pass 1 takes n operations, and after pass 1 we have one number guaranteed in the right spot. That's this number here. So now we're going to repeat, and we're going to make a second pass, and that's also going to be n operations. And when we do that, we know that the largest number is already down here in the bottom, so if we just look at this upper set of numbers, this second pass should take the largest number from here and bring it down to the bottom, which means this number is now going to be in the right spot. So 2 passes, 2 numbers in the right spot. So if we continue this for on the order of n passes, we should end up with all n numbers in the correct location in our array, and our array is sorted. So it's n passes, each pass takes n operations. That's where we get the order n squared behavior. So let's just try this with a simple array of 5 numbers. So I've got a 47, 32, 8, 16, and 23. And so let's just see what this does as we go through each of our passes. So we're going to start off, we're going to take the 47, compare it to the number below it. 47 is bigger, so we should swap these two numbers. Alright, 47 and 8. 47 is bigger, so we should swap these two numbers. 47 and 16. 47 is bigger, swap those. 47 and 23. 47 is bigger, swap those. And 47 has sunk down to the bottom of our list. Alright, now we make a second pass. 32 versus 8. Well, 32 is bigger, so we should swap those. 32 and 16, we should swap those. And then 32 and 23, we should swap those. 32 and 47, those are in the right order. And that's the end of our array. So 2 passes, we're guaranteed 2 numbers in the right spot. Third pass, 8 and 16. Well, 16 is already bigger, so we don't swap. 16 and 23. 23 is already bigger, so we don't swap. 23 and 32 are correct. 32 and 47 are correct. So that was our third pass. We've got 3 numbers guaranteed. We'll do a fourth pass, but in our fourth pass, it's going to look exactly like our previous pass. 8 is smaller than 16, so no need to swap. 16 and 23, no need to swap, and so on. And you can see that however many passes we do now, we're never going to change our data because our data is sorted. We've got an 8, 16, 23, 32, and 47. So we could have stopped the sort sooner than 4 or 5 passes. But the general algorithm, we can just do n passes. Each pass takes n operations. So a couple of things to note here. The first is if we have 5 items in our array, we make 1 pass through. It brings this first item into the lowest position, and we actually don't do 5 operations. We compare this to this. That's 1. These 2 is 2. These 2 is 3. Comparing these 2 is 4. So we've actually got 4 operations. Our second pass, we don't need to compare to this biggest number. We only need to compare these, and these. So that's actually 3 ops. Our next pass, we'll only have to compare these and these. So that's 2 ops. And our final pass, we'll just have to compare the first 2. So that's 1 op. So really, instead of n squared, it's actually 1 plus 2 all the way up to n minus 1. And this is a smaller number than n squared, right? We know that this number is actually equal to n minus 1 times n over 2, which is n squared minus n over 2, which is n squared over 2 minus n over 2. And this is a much smaller number than n squared, right? We're taking n squared, we're dividing it by 2, and then we're subtracting something else. But remember, order of complexity, we get to do 2 things. 1, we get to throw away constants. So order n squared minus n over 2 is basically the same as order n squared minus n. And the other thing we get to do is we get to look at the dominant term. In a polynomial, we get to look at the term with the highest exponent, n squared, and we can ignore that minus n. And so even though this will take fewer steps than that, the order of complexity, the growth rate, will tend to be the same for these 2 algorithms, because as n gets larger and larger, n squared becomes more and more dominant, n becomes less significant, and eventually the difference between n squared and n squared minus n gets small enough that we can ignore it. So bubble sort is a order n squared algorithm. The other thing to note is that we can make optimizations, right? For example, when we were sorting this set of numbers, we found that after 2 or 3 passes, our data was already sorted. And so we can do something like set a flag, and anytime that we swap a pair of entries, we can set that flag. And at the end of a pass, if the flag hasn't been set, we can say, hey, we're done. So we can take advantage of that. For example, if we're asked to sort an array that's already sorted, we could make a single pass, and if nothing gets swapped, we could say, hey, we're done, the data's sorted. And that would be an order n. So this has a good best case behavior of order n, but average behavior in worst case is n squared. So that's bubble sort. Tried and true, really easy to code, right? It's a pair of nested for loops for pass equals 1 to n, and then for I equals 0 to n minus 1, just compare, or n minus 2, compare element I to element I plus 1. If they're out of order, swap them. All right, so that's bubble sort. Closely related to that is an insertion sort. Well, not closely related, but similar in that it's also order n squared. So insertion sort is close to selection sort. And the difference is when we do the work. Both of these sorts, insertion sort and selection sort, these are both order n squared. And without getting fancy, we're just going to think of these as starting with an array of numbers, which is our input set, and then copying from there into a new array, which is our output set. And the goal is, when we're done with all of our copying, the output should be a sorted version of the input. But there are two ways to do this, and the difference between these ways is where we do the actual sorting. So let's talk about insertion sort first of all. So insertion sort, we're going to pick the first input and place into the output in sorted order. Alright, so here I'm going to have my input pile, over here I'm going to have my output pile. Alright, I'm always going to pick the first input, I'm going to put it into my output in sorted order. I want my output to have the smallest number on top. My output pile is empty right now, so I'm just going to put this right here. Alright, now I do another pass. I pick the first input, that's a 16, and I put it into my output pile in sorted order. Now I can't put it on top of the 10, I've got to put it below because 16 is bigger, so I put it under here. Alright, I pick the first thing from the input, that takes no work. I put it into my output in sorted order. It's got to be after the 10, it's got to be before the 16, I'll put it right there. Alright, here's my next number, 17. Comes after the 10, comes after the 11, comes after the 16. Okay, I'll put it right there at the back. Got the idea? Here's my first number on the input, 32. Comes after 10, comes after 11, after 16, after 17, goes at the back, 32. The next number is 4, that goes before the first number. There's my insertion. Here's a 51, comes after 4, after 10, after 11, after 16, after 17, after 32. There's a 51, goes right there. And we just keep doing this. So to pick the first number from the input, that's order 1. We just grab the next element from the input array. To place it into the output, that's the order n operation. Because when I want to place my 42, hey, it might be that it goes right on top, or I might have to search through here to find the first thing that's bigger than 42. Up right there. And then I've got to make room in my array to store this number, so I've got to move this somewhere, put the 42 in its place, and then have the 51. So that's an order n squared. And you know, selecting the first element, like I say, you just have an index and just say I'm going to take element 1, 2, 3, 4, 5, and so on. Putting into the output array, well, if I have my numbers like 5, 10, 15, and 20, and I want to insert a 12, well, I start at the beginning and I find the first number that's bigger than 12, which is right here. And then I need to copy all of the things from here on down, one spot down in the array. So I copy the 20 down to here, I copy the 15 down to here. Now this spot is open, that's where I put my 12. So it's that searching and then moving things down to make space that makes this an order n pass. And we have to do n passes for the n pieces of input, so that's order n squared. So that's the insertion sort. Selection sort, pick smallest input, put on top of output. With a selection sort, we do the work when we select which input number to move. So we don't just take the top number, we have to search and find the smallest number in the input pile, and then we put that on the top. So here's what an selection sort looks like. Let's find the smallest number. So 32 is the smallest, 32 is still smaller, oh, 10 is even smaller, 51 is too big, 5 is even smaller, 8 is bigger, 23 is bigger, 17 is bigger, 47 is bigger, oh, 4 is even smaller, and 11 is bigger, and 16 is bigger. Alright, 4 was my smallest number. So I select 4, and I put it in my output pile. Alright, so I did the order n operation, the selection part, in choosing the smallest number from this input pile. Then I just put it, you know, at the bottom of my output pile. Alright, now I'm going to do that again. I'm going to find the smallest number in this input pile. Well, so far that's 32. It's still 32. It's a 10. 10 is the smallest number. 51. 5 is even smaller than 10, so we'll remember that. That's bigger. That's bigger. That's bigger. That's bigger. 11 is bigger than 5. 16 is bigger than 5. Okay, 5 was the smallest number. So I'm going to remove that from our input. I'm going to put it on the bottom of our output. Alright, and we're just going to keep doing this, and every time we do this our output pile grows and our output is always sorted. We'll do one more pass. 32 is the smallest, smaller than 42. 10 is smaller than 32. 51 is bigger. 8 is smaller than 10, so we'll remember that. That's bigger, 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 bigger. Alright, 8 is our smallest number, so we remove that from our input pile, put it on the bottom of our output. So we've made 3 passes, and we have 3 numbers sorted in our output pile. So this is also order n squared. Picking the smallest input, that's an order n operation, and we do a total of n passes. And picking the smallest number, you know, if you have a set of numbers, you start off with your first number, that's your smallest, and then you just move through, and if the number that you're seeing is smaller than the number you're remembering, remember that number. And then when you get down to the end, whatever number you're remembering, that's the smallest. Now we don't need to shift this input array if we remember that's our smallest number equals 5, and let's remember its index, and let's make this a real array. So we've got a length of the array which is 6. We have 6 elements. And as we go through, when we find a number that's smaller, we remember the value of that smallest number and also its index. So we come down to the end, oh, there's a 3. That's a number 3 with an index of 3. That's even smaller than 5. 11, 25. Okay, we're done. We've gone through. We've made 1 pass. We found the location and the value of the smallest number. So we copy that to our output array, just output array bracket, you know, size plus 1 equals that number. But how do we remove this from the input array? Well, it's pretty simple. Just take the last number in the array and copy it to the index of the smallest number. So put our 25 here and change our length to be 1 less. And we've got our 3 in our output array. So now make another pass. 12 is the smallest at index 0. Here's a 5 that's smaller than 12, so our smallest is 5 at index 1. There's a 6 which is bigger, bigger, bigger. And our length is only 5, so we're only going to look at these first 5 entries. And when we're done, the smallest number is 5 and its index is 1. So we copy that to our output. Index 1, we want to remove that, so we're going to take the last number in our array, right, and the last number is at index length minus 1, that's an 11. We'll put that right here, and we'll change the length to 4. So effectively now our array is just these 4 things. And as we go through, we'll eventually find the smallest number is 6 with an index of 2. We'll add that to the output. And then we'll take the last element, the element at length minus 1, and move that into index location 2. So this will become a 25, and we'll set our length to 3. And now we're just looking on these three input numbers. So even though we're using arrays, which are kind of, you know, single-minded in how they operate, the operations are not that complex, right? Removing from the middle of an array, if we don't care about the order, easy to do. Adding to the bottom of an output array, also easy to do. So that's insertion and selection sort. Thing to keep in mind, they're both order n squared. And insertion, we do the work when we put our number into the output. Selection, we do the work when we pick our number or select our number from the input. So this term, insertion selection, tells you where the hard work is being done. Alright, so those are order n squared sorts. And they're good for a quick go-to. Insertion sort is actually how I alphabetize papers. When I'm grading homework and I need to put them into Canvas, I need to alphabetize them, and so I end up doing mostly an insertion sort. I take the first paper and I put that in an output pile, and I take the second one and put it before or after the first, and I take a third paper and put it in the right spot relative to those two I've already done, and so on. And that works well, you know, for 20, 25 papers, if you don't mind shuffling papers around, but it does get to be a fair amount of shuffling. But when I have a larger class, if I'm doing like 40 or 50 papers, I actually end up doing something else besides that. I end up doing part of what is called a merge sort. And a merge sort is going to be our first sort that's better than n squared. And it's a recursive sort. And so let me start off with an array of numbers. So I've got an array of 12 numbers here. And what I'm going to do first is I'm going to split this into two smaller arrays. Alright, so I've got 6 cards in one pile and 6 in the other. So step 1, split your data into 2 sets. If there's an odd amount of data, one set will have, you know, one piece more than the other. That's okay. Alright, so split your data into 2 sets. 2. Sort each set independently of each other. All right. Well, you know, this is where if I'm grading papers, I split the pile of exams in half, and I do my for me an insertion sort. But let's not worry about how we're going to sort each of these. Let's just sort them by using the magic of our mind and just kind of place them into sorted order. So that's that pile, and this one I'll just go 11, 16, put the 4 and 5 on top. Oh, and there's an 8 and a 42. Alright, so I've split my data into 2 piles. I've sorted each pile. Don't worry about how we do that yet. And then merge those sets into a single sorted set. Alright, how do we do this merge? It's actually really easy to do. Here's my 2 piles. The smallest number of this pile is right here. The smallest number of this pile is right here. So what's the smallest number of the entire set? It's either this or this. Right? So I'm just going to take the smallest number of these 2, and I'm going to put that into my output pile. I'll put it face down. Alright, that's it. Let's just do it again, because now the smallest pile, the smallest number in this pile is here, the smallest number in that pile is there. The smallest number of this entire set is either here or here. Whichever one of these is smaller, that's the smallest in the entire set of data. Well, that would be a 5. And same thing, now it's an 8. And now, you know, there's a 10 that's the smallest here, and 11 is the smallest here. Well, one of these is the smallest number in this untouched pile. That's got to be the 10 because it's smaller than an 11. So I take the 10 and I put it here. So all I'm doing in this merge operation is I look at the top of each pile and I pick the smallest number. 17, 23, 32, 42. And once this pile is empty, right, all my numbers are going to come from here. So 47, I don't have anything to compare it to. I'll take the 47, I'll take the 51. And just like that, by magic, my output pile is now sorted from smallest to largest. So the interleaving, the merging of these piles, is trivial. Right? This is order n. Right? If I have a total of n pieces of data, I'm going to have to take the smallest of the two piles and put it into my output. That's going to happen a total of n times. So the merging is really an order n operation. And depending on what language you're working in and how you're storing this data, splitting our data into two sets is basically an order 1. It's not really going to take more time for more data. If we have an array, we know it's got 1,000 things. Well, we just take elements 0 through 499. That's our first half of the array, and 500 through 999. That's the second half of the array. So that's kind of like an order 1. And so this is a pretty efficient sort, but we still have to deal with this question of how do we sort each of those sets. Remember, we started with a big set of data, we split it in half, and we said, okay, sort this half, and then merge them together. So how are we going to sort this half? And the answer is use a merge sort. So this is recursive. We're going to split our data in half, and then we're going to use merge sort to sort each of those halves, and then we're going to merge them back together into a single set. Well, when we've done that split, let me go back to my first half, and I've got, you know, a set of 6 pieces of data. I need to sort it. Well, what does a merge sort look like? I will split it in half. I will sort this pile, and I will sort this pile, and then I'll do my merge. So I do a 4, I do a 5, I do an 8, I do a 16, I do a 17, I do a 32. There we go. Sorted pile. And then to sort this half of 6 cards, I'll do exactly the same thing. Well, how do we sort this pile of 3 cards? We use a merge sort, so split it in half. So, you know, 1 and 2. Sort each half. This is already sorted. This happens to be sorted. Pick the smallest from each one. And there we go. All right, recursion, remember, we need a base case. If set has only one element, then you're done. Don't have to do any work. So if we have 2 numbers, like here's a deck of 2 pieces of data, what are we going to do? We're going to split it into 2 pieces. We're going to merge sort each of these. Well, when we try to merge sort this, we're going to see the base case. Hey, there's only one number in here. We're done. We're going to try to merge sort this set of data. There's only one number. We're done. So sorting these will require no work, and then we merge these together, 23, 42. Hey, and we're done. We just sorted our set of 2 cards. And if we had 4 cards, we do that twice. We interleave the 2 sets of 2, and when we're done, we've got our sorted set of 4 data, and so on. All right, so what's the order of complexity for this? Well, each of these operations, the interleave takes n operations, Splitting the data is order 1. That's just a constant. We can ignore that. So the question is, how many passes? Right? Each time that we say merge sort, we're going to branch off. We're going to do 2 smaller sorts. And for each of those 2 smaller sorts, we're going to branch off. We're going to do 2 smaller sorts for each of them. So we're going to get 4 sorts. So we're going to end up with n sorts, which is going to look like n times we have to do this order n merging. But each of those sorts is smaller. In fact, it's half as big as the prior sort. And if you work through the math, you get some telescoping series. What you'll end up finding is that this is order n log n. And that's a really nice order of complexity. That means that if we have 1,000 times more pieces of data, it's going to take us, 1,000 times whatever log of 1,000 is, which is about 10, times to perform this sort versus on a smaller set of data. So 1,000 increase in the amount of data, total time that it goes up is 10,000 as opposed to 1,000 squared, which is 1,000,000. So significantly better than order n squared. So that's merge sort, and it's not a bad sort to code. The hardest part in C is dealing with arrays, because arrays are kind of funny, right? They're pointers to memory locations. So splitting our data in half and working with the second half of an array, it's not impossible. It's not even difficult if you can keep straight what you're doing with the indices. But if you haven't done it before, it's fairly complex and confusing. But this works really well in other languages that treat arrays as, sort of their own data type, and let us do things like, pull off half of an array and put it into another array, and so on and so forth. So that's a nice n log n sort, and a lot of sorting algorithms that we find in other systems will use something like a merge sort internally, because it is very efficient. All right, so let's look at another sort. This one is called a quick sort. And quick sort is a really different kind of sort. It's, I think, one of the more confusing ones to work with when you first encounter it. But we're going to look at an example of how we use quick sort to basically go through a set of data, and our goal is to move some of the things in our set around so that we basically split our problem into 2 smaller problems. So similar idea to what's happening in a merge sort. So let me just make a set of numbers to work with. So 20, 40, 11, 16, 23, 28, 1, 50, 9, and 18. All right, so quick sort, we have a series of steps here. So step 1, choose a pivot, and I'm going to circle the pivot, and typically we'll use for a pivot the last number in the array or in the list. So we're just going to pick 18 to be our pivot. And there's all kinds of analysis we can do as to what makes a good or poor choice for a pivot, but for us, we're just going to say we're always going to take the last number as a pivot. All right, what does this mean? We are going to move some things around in this array so that when we're done, this 18 is going to be somewhere in this list, and everything to the left is going to be smaller, everything to the right is going to be bigger. Right? So the choice of pivot makes a difference to how our passes behave. We're just going to pick the last thing as a pivot. So we want to move things around in here so that when we're done, the 18 has the property that everything to the left of it is smaller, everything to the right is bigger. All right, And we do this with a single pass, and this is an order n pass. And here's what we do. We begin on the left, and we start moving over, looking for the first number that's bigger than our pivot. Alright, so we're going to start off, we're going to look at the 20, and we're going to stop right there, because 20 is bigger than 18. Now we're going to go to the right, and we're going to start moving in this way, looking for a number that's smaller than our pivot. Well, the first number we look at is 9. That's smaller than 18. Hey, we're done. Okay. So we found the first number bigger than our pivot, the first number smaller than our pivot, and we're just going to swap those. So we're not going to move anything else in the array right now. We're just going to swap those two numbers. So this is going to be a 9, a 40, an 11, a 16, 23, 28, 1, 50, here's where the 20 goes, and here's the 18. And I'm preserving our arrows so we have a pair of pointers showing how far we've moved from each end of our data. And now we're going to continue. We're going to start moving in this way and try to find the first number that's bigger than our pivot. And again, the first number we encounter is 40, that's bigger than our pivot. So now we're going to come over here and we're going to move to the left and try to find a number that's smaller than our pivot. Well, 50 is bigger, but 1 is smaller. Alright, so as soon as we find the number that's bigger than our pivot and a number that's smaller than our pivot, we stop. And we're going to swap these. And so now our data is going to look like this. There's a 9, the 1 comes over here, 11, 16, 23, 28. The 40 goes in place of where the 1 was, 50, 20, and there's our pivot 18. And our arrows were here and here. We're going to do this again. We just keep doing this. Move over to the right and look for a number bigger than our pivot. It's not there, it's not there. Oh, there's a number bigger than our pivot. And now move over to the left and try to find a number smaller than our pivot. Well, not smaller, not smaller, but at this point our arrows have collided with each other. Alright, so we're done at this point. And what we do now is where these arrows collided, we swap that with the pivot. And so now our final array looks like 9, 1, 11, 16, 18, 28, 40, 50, 20, and 23. Now I'm going to draw a box around this former pivot that we just moved in place of where our arrows met. And now let's just look at what we've done. We have rearranged a few things in our lists. We only moved in one number at a time, and we moved this way one number at a time, and we did that until our arrows met. So the total amount that we're moving our arrows is n times, right? And sometimes we pause and make a swap, and then we continue moving our arrows. And when we find two numbers out of place, we pause and we make a swap, and we continue moving the arrows. But worst case, if we did a swap every time that we moved our arrows in, it's still an order n operation. The amount of work we do each time we go in is a little bigger because we have to do a swap of two numbers in our array. But this is order n. And what has happened after we've done this order n operation, whatever number the pivot was, everything to the left is smaller, everything to the right is bigger. Now these are out of order, right? These 4 numbers, and these 5 numbers can be out of order. But we know that everything over here is bigger than 18, everything over here is less than 18. So we know that 18 is in the correct spot in the final array. And all we have to do is sort this set of 4 numbers and this set of 5 numbers. And once we do that, the whole array will be sorted because the 18 is already in the right spot. Alright, so we're almost done. We do an order n operation to move the pivot into its correct spot. And then we have to sort the things to the left of the pivot, and then we have to sort the things to the right of the pivot. And how do we do those two sorts? We use a quick sort. So it's another recursive sorting algorithm. And the quick sort, you know, when we quick sort this, we'll take 16 as our pivot, and we'll come along with 9 and 1 and 11, and those will all be sorted, so not much interesting happening there. When we sort this piece, we'll start with a 23, and the 28 will be too big, and the 20 will be too small, so we'll swap 20 and 28, and so on. And this is similar to merge sort because in general, even though it's an order n operation to sort, you know, this one pass through the n pieces of data, the amount of times we have to do this, you know, we'll do one pass to get down to these two half lists, and then we'll do another pair of operations to sort each of those. But these lists that we're sorting using quick sort are getting smaller and smaller. And so this whole thing ends up being order n log n. So when you take an algorithms class, you'll spend a fair amount of time actually proving these orders of complexity, really digging into the stuff I'm waving my hands at, where I'm saying like, yeah, it's going through n times, but the list get cut in half each time, so it ends up being n log n. It's true, but you'll actually go through proving that in something like an algorithms course. And that's a good thing to go through at some point, but it's not something we need to worry about here. So that's a quick sort. And quick sort has an interesting characteristic, right? Merge sort, remember, we're cutting our list in half, sorting each half, putting them together. So that's pretty certainly n log n, but quick sort has a potential pathology, which is the way that this is working is we pick our pivot and we eventually place the pivot into the middle of the list, and everything to the left is smaller, everything to the right is bigger. But what happens if that pivot is already the biggest number in the array, or close to the biggest number in the array? If this number ended up going like right here, well, when we say, okay, that number's in the correct place, we have to sort these two numbers. Well, that's easy, but we have to sort all of these numbers. We haven't really cut our problem in half. We took it from sorting all of these numbers to sorting these numbers. And so it turns out if your data is sorted to begin with, or close to sorted to begin with, this can break down to being more like an order n squared. So sometimes quicksort algorithms, what they do, they jumble up your data before they begin sorting. Just in case your data happens to be sorted, they'll randomize it. And you'll actually get better performance that way than if you started with something that was almost sorted. Now bubble sort, remember, if your data is almost sorted to begin with, you can get something closer to order n. Quick sort, if your data is sorted or almost sorted, you can actually end up with something closer to n squared. You get worse behavior that way. Alright, let me do one more pass of quick sort on a different set of data, and we'll go through this one pretty quickly, but just to give you one more visual representation of this. So let's take this set of 9 numbers and apply a quick sort. So here's our pivot. We're going to start here and move to the right till we find something bigger than 15. So that's okay, that's okay. There's a number bigger than 15. Now we'll move to the left and try to find something smaller than 15. We stop right there. These two numbers have to be swapped. So we get a 2, 5, 1, 8, 10, 16, 20, 40, 15. 15 is our pivot. We moved in here. We moved in here. Now we continue moving from the left. This is smaller than our pivot. This is smaller than our pivot. We come up here and our arrows have collided. And so we're done. And this is the number that we're going to replace with the pivot. So we swap these two, and now we have a 2, 5, 1, 8, 10, 15, 20, 40, 16, and here's the number that's in the right place. So if you don't do all the talking and hand waving while this is going on, it's a pretty quick thing to go through one pass of quick sort. but, you know, the hand waving hopefully helps you see what's going on. Alright, so that's quick sort. Couple of more sorts to talk about. First one is a radix sort. And radix sort is good for alphabetizing, and we can sort numbers if we think of numbers as being words that we can alphabetize. So let's use a radix sort to sort some 3-digit numbers. So I'll do a 231, 222, 240, 400, 399, 199, 287, 519, 411, and 23. Alright, so here's a list of 10 numbers. They're 3-digit numbers. If it's, you know, not a 3-digit number, throw some zeros in the front. Alright, radix sort works by just making a series of passes through our data and sorting based on 1 digit at a time. And it's slightly counterintuitive, because if we have a set of numbers and we try to sort them, or a set of anything we're trying to sort, we usually, you know, the digits on the left are the most significant thing in our sort order. We know that this thing that starts with a 5 is going to be the biggest number of all of these. So normally, you know, we give those the most weight, but with a radix sort, we actually begin by sorting with the least significant digit. So first thing we do is we sort by this least significant digit here. So we're just going to look at the ones place. And an important part of how we sort by that digit is if two things have the same digit, we can't change their order. So this has to be a non-disturbing sort, meaning that, you know, if two things are out of order, yeah, we've got to swap them. But if two things are not out of order, we're not allowed to change their position relative to each other. Alright, so how are we going to do that? Well, an easy way to do that, since we have 10 digits, is to make 10 passes through this data and pull out all the numbers that end with a 0, then all the numbers that end with a 1, a 2, and so on and so forth. So let's do that. Let's make our first pass based on the ones digit. Let's go through first and find all the things that end with a 0. So we've got a 240, we've got a 400. That's it for things that end with a 0. Let's find all the things that end with a 1. That's a 231 and a 411. All the things that end with a 2, there's a 222. And that's it. Find anything that ends with a 3, that's a 023. Anything that ends with a 4 or a 5 or a 6 or a 7, there's a 287. Anything that ends with an 8, anything that ends with a 9, there's a 399, there's a 199, and there's a 519. Alright, so we've sorted this original list by least significant digit, and we did it in a way that, you know, if these two things were in this order, they're still in that order out here. Okay, so that was one pass. Now we're going to sort by this middle digit. And we can do that by making 10 passes through our data. First, find anything that ends with has a 0 in here. So there's 400. Now find anything with a 1 in that middle position. There's 411. There's 519. Anything with a 2, 222, 023. Alright, anything with a 3, there's a 231. Anything with a 4, there's a 240. Right, so I'm just looking at this middle digit, looking for anything that has a 5 in that middle position. Anything with a 6. Anything with a 7. Anything with an 8. And there's a 287. And then finally anything with a 9 in that middle position. There's a 399. And there's a 199. Alright, and now I got to do one more pass, and I'm going to sort by most significant digit. And so I'm going to go through, find anything that has a 0 in the beginning. There's a 0, 23. Anything with a 1 in that first position, there's a 199. Anything with a 2, there's a 222. And there's a 231. And there's a 240. And there's a 287. Anything with a 3 in the first position, there's a 399. Anything with a 4, there's a 400, 411. Anything with a 5, there's a 519. And anything with a 6, 7, 8, or 9, there isn't anything in there. So here's our final set of 10 numbers. And guess what? It's perfectly sorted. Alright, so this is called a radix sort. I believe it's similar to what was used in early tabulating machines like Hollerith machines that were sorting and tallying census data back in the late 1800s. It's a pretty easy sort to mechanize, in code in particular, right? And the order of complexity looks shockingly good, right? The number of passes we have to make is basically the number of digits in our number. And even if we use this sort of very heavy-handed approach to sorting, where we make 10 passes through, pulling out everything that ends with a 0, 1, 2, 3, 4, and so on, if we use this for numbers, 10 digits, so you've got 10 passes, and the number of digits that we might have, well, if we are working with 32-bit integers, those go up to 1 billion. So let's say 10 digits. Well, that's order of 100. Times n. Right, so however many pieces of data we have to go through n, all n pieces of data 10 times to create this next column, and we have to do that n times to go through all n digits. So yeah, this looks like order 100n, and remember we said we can throw away constants, so this looks like an order n sorting algorithm. And you know, the best we've gotten was n log n with merge sort and quick sort. Is radix sort far superior? Is it actually an order n algorithm? And this is an interesting case because, you know, order n is certainly better than order n log n as n approaches infinity. But n does not approach infinity here, right? We use the fact that we're only working with 10-digit numbers that bounds the amount of data that we had. If we're only working with 1 billion numbers, right? Suppose we look at bubble sort on n pieces of data. Well, if we say there's only 1 billion pieces of data, we could say a bubble sort. Well, if we have 1 billion numbers to sort, each pass takes 1 billion operations. And in each of those passes, we have to do n operations. So we could say, you know, our bubble sort is no worse than 1 billion n. And we could say, hey, and that's kind of the same thing as order n. So we could say, hey, a bubble sort's actually order n. But that's bogus, right? Because this complexity is talking about as the amount of data grows. And we restricted our amount of data here to 10-digit numbers when we did this calculation. Order n log n, well, what's the log base 2 of 1 billion? It's approximately 40, so n log n, if n only goes up to 1 billion, is actually order 40n, whereas this is 100n. So even on that comparison, it looks like this is worse than a merge sort or a quick sort. So you got to be a little careful with these orders of complexity, right? Think of them as asymptotic limits. As our data size grows to infinity, how does the complexity, the time complexity of our problem grow? That's really what we're looking at. And if we fix our problem to, you know, something no bigger than a certain finite size, these can be deceptive measures. All right, so that's a radix sort. The last thing we want to talk about is called a heap sort. And heaps are their own subject of discussion in data structures. So what is a heap? A heap is a tree-like thing that has two characteristics. One, it's shaped like a heap. Two, it satisfies the heap property at every node. Alright, that's a pretty unsatisfying definition. We'll add some details to that now. So a heap is a tree-like thing that has two characteristics. It's shaped like a heap and it satisfies the heap property. What is the heap property? So there's two types of heaps. A max heap and a min heap. So the heap property for a max heap says each node is bigger than all its children. A min heap says each node is smaller than all of its children. And being shaped like a heap means every level is full, except possibly the deepest, which is full from left to right. Alright, so let me draw pictures. This has the shape of a heap because every level is full except the deepest level, and the deepest level is full from left to right. If I add another node here, it still has the shape of a heap. Still has the shape of a heap. If I want to add one more piece of data, I can't put it off of this node or that node or that node. I can't put it down here. It's got to go over here. If I want to add another piece of data, it cannot come off of this node, that node, or that node, and it cannot be a child of this node. It's got to go one spot and one spot only, right here. So to have the shape of a heap, every level has to be full. 1, 2, 4 nodes, except possibly the deepest node, and the deepest node has to be filled in from left to right. Alright, so this has the shape of a heap. So does this, so does this. In other words, every time you add a new piece of data, it's got to go on the deepest level in the first leftmost spot that's available. Alright, that's the heap shape. Heap property, let's just talk about max heaps. And in a max heap, every node has to be bigger than all of its children, including grandchildren and great-grandchildren. So let me show you an example of a heap. 75, 23, 12, 10, 18, 9, 11, 4, 1, 13. Alright, this is a perfectly valid max heap. So it's got the shape of a heap. Every level's full except the bottom, and the bottom's filled in from left to right. And if I look at any node, 75 should be bigger than all of these other nodes. 23 should be bigger than all of these. 18 bigger than 13. 10 bigger than 4 and 1. 12 bigger than 9 and 11. It's a max heap. Right? So it's like a sloppy tree. There's no significance to whether something is on the left or right. Right? In this case, the left child is bigger than the right child. In this case, the left child is smaller than the right child. That's completely irrelevant. The only thing that matters is the relationship of the children to the parent. So in a max heap, all children have to be smaller than their parents or their parents' parents, and so on. Alright, so that's what a heap is, and we're going to concentrate on max heaps for the rest of this. then we'll touch on min heaps at the end. They're symmetric. All right. If we have a max heap, largest number is always at the root. That's guaranteed to be the largest number. Why? Because if this number was bigger, the heap property would fail right here. 75 has to be bigger than both of its children. And each of those children has to be bigger than its children. Well, greater than is a transitive relationship. If A is bigger than B and B is bigger than C, then A is bigger than C. So 75 has to be bigger than everything in the tree. So the largest number in a max heap is always at the root. So heaps are good for storing data and then retrieving it in sorted order. In this case, saying, hey, I want to pull out my data from largest to smallest. Well, where's the largest number? It's just at the root. Really easy to find. All right, now suppose I remove this 75 from my heap. So I put my 75, let's do an output. So I find the largest number, I print it out or do whatever I'm trying to do with it. I no longer have a heap, because this thing, if there's no root, it doesn't have the shape of a heap. It doesn't even look like a tree. It looks like two trees. All right, I can choose to replace this 75 with some other node, but there's really only one choice. For example, if I moved my 11 up here to the root, and I took away the 11 here, it's not going to have the shape of a heap. Or if I move the 9, or if I move the 18. There's really only one node I can move up here and still have the shape of a heap, and that's the deepest level rightmost node. So I'll take that 13 and put that up in the root. Well, now it's got the shape of a heap, but it might violate the heap property. So I check. Look at 13, see if it satisfies the heap property. Is 13 bigger than both of its children? No. It's bigger than 12, but it's not bigger than 23. So I'm going to swap with the largest child. I'm going to put 23 up here and bring 13 down here. And then I'm going to repeat. Is 13 bigger than both of its children? Well, no, it's not bigger than both of its children, so I'm going to swap with its largest child. So I'll put 18 here and bring 13 down here. And is 13 bigger than both of its children? It has no children, so it satisfies the heap property, and we're done. And so our new heap looks like this: 23, 12, 9, 11, 18, 10, 13, 4, 1. It's got the shape of a heap. Each node satisfies the heap property. And now the largest number in our collection is 23. All right, so let's write these steps down. Max heap. Largest node is at the root. All right, replace root with the last node in the heap. And the last node in the heap is deepest level rightmost node. So the node that's deepest down and furthest to the right. If our heap looked like this would be the last node, because it's the deepest level and the rightmost. If our heap looked like this, the last node would be 11. So, go down as far as you possibly can to the deepest level and just pick the rightmost node. That's the one that we move up to the root. And then we do what's called downheap. And downheaping means start at root. If the heap property is satisfied, then we're done. Otherwise, swap with the largest child. Move down and go back and repeat. All right, so let's downheap this tree. Let's remove the 23. So we'll take that out. We'll take the last element, the rightmost element on the deepest level, which is a 1, put it up there, and now we'll down heap. 1 is not bigger than its children, so swap with the largest child. This becomes an 18, this becomes a 1. 1 is not bigger than its largest child, so swap with the largest child. This becomes a 13 and a 1. And this has no children, so it satisfies the heap property, and we're done. And now 18 is the largest number in our heap. We could remove that and then replace it with the last number in our heap, which is a 4, and down heap. 4 is not bigger than both children, so replace with the largest child. 4 is not bigger than both children, so replace with the largest child. And 4 has no children, so we're done. And we just keep doing this. Alright, so that's a max heap. It's really useful if you have data that you've stored and you want to pull it out in, say, decreasing order. An example where this happens inside an operating system would be a priority queue. You have a bunch of jobs waiting for the CPU. You schedule them based on priority. System processes get higher priority than user processes, which get higher priority than, deep background processes. So when it's time to find a new process to get a chunk of CPU time, you want to very quickly find the process with highest priority that's ready for the CPU. Well, heap is an example of a place where we would do that kind of thing, right? We could store our jobs in a heap, and anytime we want to find the highest priority job, just pull out the root. And then, while that job is being processed, we can casually go ahead and find the last node, put it up, down heap, and be ready for the next time we're ready for the largest number. We can pull that out. All right, how do we insert into a heap? So let me make another heap. Oh, I gotta fill this in now. Alright, so there's a sloppily drawn max heap. Let's insert something into it. So what should we insert? Let's insert, I don't know, let's do a 17. Alright, we kind of do the opposite of removal. First, we put the 17 so that it's the last thing in the heap. So go down to your deepest level, go all the way over to the right, put your new number right there. And then we do an upheap. So how does upheaping work? Well, look at this node's parent, see if it satisfies the heap property. If it does, you're done. Is 3 bigger than both of its children? No. So let's swap. Let's put the 17 there and the 3 here. So now we're sitting here. Look at its parent, see if that satisfies the heap property. Is 15 bigger than both of its children? No. So swap 15 with the largest child, which is 17. And now go to that node's parent. Does 20 satisfy the heap property? Yes, 20 is bigger than 17. 14, we're done. And we've got a heap. It's got the shape of a heap, and it satisfies the heap property. And as soon as we know that this node's bigger than both of its children, we don't have to do anything else, because we haven't monkeyed with this, we haven't monkeyed with any of that. Right? So we start from the point where we make the change, which is that rightmost position on the deepest level, and we work our way up until we either get to the root or we find a node that satisfies the heap property. And then we're done and we've got a heap again. So what is order of complexity? Right? Pulling out the largest node, order 1, but we need to down heap. We need to take this last number, put it up here, and then down heap. But how much work do we have to do to down heap? Well, each time that we move down, we go one level deeper. So the worst case number of steps we have to go down is the height of the tree, which is order log n. And when we insert, we take our new number, we put it in the last position. Well, that's easy. And then we have to upheap, and we may have to upheap, worst case, the number of levels in the tree. That's the height of the tree. And since this has the heap shape, it's nice and fluffy, it's filled in, the height of the tree is order log n. So insertion and removal are order log n, which is pretty nice. So searching for the largest number in a max heap or the smallest number in a min heap, order log n. Alright, so this was all max heap. Min heap works exactly the same way, except the heap properties at each node is smaller than both of its children. And when we're down heaping, if we have to make a change, we swap a node with the smallest of its children instead of the largest, so that the heap property as each node is smaller than all of its children. And when we're done and we have a heap, the smallest number in the entire collection is at the top. So we can pull things out from smallest to largest. Alright, two more things to discuss with heaps. The first is building a heap. Where we have a set of data and we want to store it in a heap inside our computer. So let's say we have a set of numbers, 10, 5, 20, 23, and 11. And we want to build a heap. Well, we could simply start with an empty heap and just add these one at a time. So we start off with the number 10. Well, we have an empty heap, so 10 just becomes the root. Now we want to add a 5, and we're still doing a max heap. We want to add a 5, so we put it in the last position, and we check its parent. 10 satisfies the heap property. We're done. So we've added that, we've added that. Let's add the 20. So put it in the last position, check its parent. Does it satisfy the heap property? No, 10 is not bigger than both children. So let's swap with the largest child. And we've got a heap. Alright, let's add a 23 to our heap. Put it in the last position. Parent violates the max heap property, so let's swap 23 and 5. Go to 23's parent. 20 violates the max heap property, so swap with the largest child. There's our 23. And now we've got an 11, and we want to add that to the last position, so that goes over here. Its parent 20 satisfies the max heap property. So our heap looks like this. Right, perfectly valid max heap. And since inserting each of these is order n, you know, nominally n log n operations to build a heap, and then log n to remove or to add new things. But there's a process we can use for building a heap, which is called heapifying. And heapifying works like this. Suppose we want to build a heap containing a sort of set of numbers. Well, we just take those numbers and we put them in the shape of a heap. So suppose our numbers came in this order: 20, 10, 15, 11, 40, 60, 80, and so on. We just throw them into the shape of a heap. And I happen to have, you know, a full bottom row, but that's not necessary. We put them in the shape of a heap, and that's, you know, one of our requirements, but this definitely will not satisfy the heap property unless we happen to get our numbers in just the right order. So, you know, I can see right here, this violates the max heap property, this violates max heap, this violates max heap, and so on. So what we do is we make an adjustment. We do what's called heapifying. And heapifying works as follows. So start with rightmost node on the deepest level. So we're going to start with this 6, and we're going to make an adjustment, and then we're going to go to the 101, make an adjustment, and move our way over here to the 23, and then when we're done, we're going to come up one more level and make an adjustment here, and so on, until we're up to the root. And the adjustment we make is to check that node for the heap property. Check heap property and down heap if needed. So, you know, instead of inserting each thing one at a time and down heaping, we're kind of inserting everything into the tree at once, and then we're going to go through into our down heaps. But this is going to be significantly more efficient. Alright, so let's start with a 6. Does it satisfy the heap property? Well, yeah, because it's got no children. How about 101? Yes. 91, 77, 85, 16, 120, 123. Each of those satisfies the heap property because they have no children. So we don't have to do any work for that set of data. Well, we have 15 pieces of data in this heap. 1, 2, 3, 4, 5, 6, 7, 8 of them. We don't have to do any work. So half of our problem we get for free. Alright, let's move up to this next level. Here's our 80. Does that satisfy the max heap property? No, so let's swap it with the largest child. There's a 101, there's 80. Now let's go to the 60. It doesn't satisfy the max heap. Swap with the largest child. So there's 91 and 60. 40 also fails, so swap the 40 with the 85. And 11 fails, so swap it with the 121. Alright, I just did another quarter of our data. 3/4 of my data is in these bottom 2 levels. That's the way that trees work, binary trees. Half our data down here, a quarter of our data here. 3/4 of our data, and half of it I didn't have to do any work. A quarter of it, worst case, I had to do one operation. So this is not n log n. This is going to be quite a bit better because, you know, half our data takes no work. A quarter of our data takes one operation. So for 3/4 of our data, we're doing on average less than one operation per piece of data. Alright, now we come up here to the 15, and 15 violates the heap property. Swap with the largest child. And 15 violates the heap property. Swap with the 80. And we're done. Come over here to the 10. 10 violates the heap property. Swap with the largest child. 10 violates, so swap with the largest child. And we just finished this next row, and worst case we had to do 2 swaps. And now we come to the root. 20 violates the heap property, so swap with the largest child. 20 violates, so swap with the largest child. And 20 violates again, so swap with the largest child. And we're done heapifying. And 23 is bigger than both children, 40 is bigger than its children, 91 is bigger, 80 is bigger, 101 is bigger than its children. What number did we put here? 85 is bigger than its children, and 121 is bigger than its children. We've got a max heap. And we had to do very little work. And it turns out that heapifying ends up being order n. So n pieces of data, we can build a heap in roughly n operations. So extremely efficient. Alright, so that was one thing I wanted to finish up with on heaps. There's one other aspect we need to talk about, which is how to implement a heap. And implementing a heap, I mean, it's easy on paper because, you know, paper is magic. But these things that we're describing, for example, taking a node and checking its parent, well, we would need some kind of back pointer to get from a node to its parent, because normally we have pointers from a node to its children, but this would require a more complex structure so that we can say, okay, who's the parent of this node, and somehow get back to this 101. That's one complication. Second complication is knowing where this last node in the heap is. Right, getting down to this deepest level and moving to the right, well, we would need some kind of pointer to keep track of that. We could say, you know, okay, this is the let me show you an example. If we have a heap like this, right? We could keep a pointer which says, okay, this was the deepest node in the rightmost position. So when we want to add a new node, we should go up to its parent and then come down to the right. So we could add a new node there and keep a pointer saying, okay, this is the last node in the heap. But now if we want to add another node, we need to go to the last node, go to its parent, come down to the right, and then come down to the left and add a new node there. And we're going to need some kind of probably recursive traversal algorithm to be able to find this deepest node in the tree. So implementing this with our traditional tree-like structure is kind of a pain, but it turns out that implementing a heap with an array is a really easy thing to do. And there's one trick, and if you hate arrays in C, you'll like this trick. The one trick is we don't use index 0. We only start from index 1. So let me put some elements in here. And let me draw a picture of a max heap. So here's 40, 20, 30, 11, 15, 29, 8. And so let's store this. And we're going to store this in our array by putting the root at index 1 and then just doing a breadth first traversal. So move down one level and go from left to right. So here's our 20 and our 30, and then we'll have our 11, our 15, our 29, and our 8. And we'll keep a number of nodes as an index counter. So we'll say we've got 7 nodes. So that's what our heap looks like. Okay, so we can do the things that we need to do with heaps very easily with this type of data structure. Where's the root? So let me call this array heap. Root is heap index element 1. That's the 40. Last node is heap bracket num nodes. Num nodes is 7. Heap bracket 7, that's the last element in the heap. Add a new node. Just save our new node at heap bracket plus plus num nodes. So if I want to add a new number, like say I want to insert 25, increment num nodes to 8, store your number at heap bracket 8. And that represents putting a 25 right there. Alright, remember I have to upheap. So I need to be able to find my parent. So the parent of heap bracket I is what? Well, the parent of this node is 11. Well, this node is heap bracket 8. Its parent is heap bracket 4. 11 is heap brackets 4. Its parent, 20, is heap bracket 2. And this node 15 is heap bracket 5, and its parent is also heap bracket 2. So the parent of heap bracket I is just heap bracket I over 2. And if I is odd, we just, round down. So the parent of the 5th element would be heap bracket 2. The parent of the 4th element would be heap bracket 2. So who's the parent of 29? 29 is the 6th element. It should be heap bracket 3. That's a 30. Hey, that's the parent of 29. So moving up the heap, very easy to do. Right? If you want to find the parent of the element in index I, it's just the element in index I over 2. And moving down is also easy. The left child of heap bracket I is heap bracket 2I. So who's the left child of 20? Well, 20 is at index 2. The left child should be at index 4. That's 11. Who's the left child of 40? 40 is at index 1. Left child should be at index 2. That's the 20. And the right child of heap bracket I is heap bracket 2I plus 1. So who's the right child of the root? Well, the root is at index 1. The right child should be 2 times 1 plus 1. That's 3. That's a 30. That's the right child. Who's the right child of 30? It's at index 3, so 2 times 3 is 6, plus 1 is 7. The right child of this should be at index 7. That's an 8. That's the right child. So moving up and down the heap, all we have to do is simple index arithmetic. To move up, divide by 2. To move down, multiply by 2 for the left, multiply by 2 and add 1 for the right. The root is always index 1. The last node is always index whatever num nodes is. And so if you want to add a new node, you just put it in the spot after a number of nodes and increment that counter that says how many nodes we have. So this is an interesting case where we can go back to arrays, right, which we learn in like our first programming course, and they actually work better than these sophisticated pointers and dynamic memory allocation for this particular structure, which is a heap. So that's a fun thing to code, and we'll play around with some aspects of that in the practice problems. All right, that's the lowdown on sorting and searching. All right, thank you.